We're now going to talk about the Laplace equation. The best way to introduce the Laplace equation is to talk about the steady-state heat equation. You can see before you the heat equation in one dimension where we've held the ends of a metal rod fixed at temperatures T1 and T2. To find the steady state, you will recall that we were looking for a solution where the time derivative was 0. This meant that we had that uxx had to be 0, and the boundary conditions remained that u at the left endpoint was t1 and u at the right endpoint was t2. And since this is a steady state, I will refer to the steady state temperature as maybe u bar. This boundary value problem that you see before you is actually the Laplace equation in one dimension. We solved for u bar by recognizing that if two space derivatives of u bar is 0, then u bar of x must be a line. On the left edge, u of 0 is equal to c1, which is just t1. And on the right edge, u of L is equal to T1 plus C2L, which is equal to T2. So C2 is equal to T2 minus T1 over L. And so u bar, our steady state temperature, is equal to T1 plus T2 minus T1 over L times x. And that's just the line that connects the temperatures T1 to T2. And now we have solved the Laplace's equation in one dimension. But we're going to be more interested in the Laplace equation in multiple dimensions. In 2 dimensions, you can see that Laplace's equation is a time derivative of u is equal to the diffusion coefficient alpha squared times the sum of the 2 second derivatives of u in space, also known as the Laplacian of u. Now, because we have 5 derivatives for this equation, we're going to need 5 initial or boundary conditions. In particular, because we have 4 derivatives in space, we're going to need 4 boundary conditions. Laplace's equation in 2 dimensions is going to describe the heat flow in a thin metal plate that you can see pictured on the right. On the bottom of that plate, we're going to hold the temperature fixed at some function T1 of x. On the top of that plate, we're going to hold the temperature fixed at T2 of x. On the left side, we'll hold the temperature fixed at T3, possibly depending on y. And on the right side, we'll hold the temperature fixed at T4, also possibly depending on y. So those 4 boundary conditions will correspond to the 4 spatial derivatives. The initial condition will be u of x, y, comma 0 is equal to some function of x and y. We now want to find the equilibrium or steady state of this equation. So because the time derivative is 0 at the steady state, then uxx plus uyy will have to equal 0 on that interval where x is between 0 and a and y is between 0 and b. We will still have that u of x 0 will be some function T1 of x, and u of x b will have to be some function T2 of x on the top of that plate. Here we're going to let x vary between 0 and a. We'll also have that u of 0y on the left edge of the plate is T3 of y, and u of ay on the right edge of the plate is going to be t4 of y. And this will be for y's between 0 and b. And this partial differential equation, which relates the space derivatives of x and y, is known as Laplace's equation in 2 dimensions. I will remind you of the definition of the Laplacian, which is del, or grad squared, is equal to the sum of the second derivatives in space. So Laplace's equation is generally written as del u is equal to 0. And besides being representing the steady state heat equation, it also has applications in electrostatics, where the charges of a metal plate will be held fixed on the edges of that metal plate, like the diagram that you see on the right. We now want to solve Laplace's equation on a rectangle. So we will solve this using separation of variables. We're going to assume that our function u of xy is a function of x of x, times a function of y of y. So plugging that solution back into the equation, we get x double prime of x times y of y plus x of x times y double prime of y is equal to 0. So I'm going to move all the x's onto one side, all the y's onto the other side, and I'm going to divide by x of x, y of y. So what I have on the left side is a function of x, and on the right side is a function of y. And as you recall from before, if I have a function of x that for every x equals a function of y for every y, then both of those functions must equal some constant, and I'll call that constant lambda. Okay, so there are now 2 resulting ordinary differential equations that I can get from this relationship. I have that y double prime of y plus lambda y of y is equal to 0. On the boundaries, I'll have that y of 0 is equal to 0 and y of b is equal to 0. And those correspond to the boundary conditions that u of x 0 is 0 and u of x b is 0. I will also have x double prime of x minus lambda x of x is equal to 0. And I'll have the boundary condition that x of 0 is equal to 0, which corresponds to the boundary condition u of 0, y equals 0. You can see that there's one more boundary condition that is non-zero, u of ay is equal to a function of y, and we will use that one later. So now we want to look at problem 1. Problem 1 says that y double prime of y plus lambda y of y is equal to 0. And this is a problem that we've actually encountered before. You'll recall that if I add the boundary conditions where y is 0 on both ends, then the solution is that the eigenfunctions y sub n of y are sine of n pi y over b, and the eigenvalues lambda sub n are n squared pi squared over b squared. So now we want to move on to problem 2. Here we would have that x sub n double prime of x minus n squared pi squared over b squared, which is lambda sub n, times x sub n of x is equal to 0. And I have that x sub n of 0 is equal to 0. Well, because of the minus sign that you see, we can guess that x sub n of x is equal to a sum C1 of cosh of n pi x over b plus C2 sinh of n pi x over b. We could have also written the solution as x sub n of x equals C1 e to the n pi x over b plus C2 e to the minus n pi x over b. But you'll see in a moment that writing this as the sum of sinh and cosh will make dealing with the initial or the boundary conditions a little bit easier. Okay, here we have that x sub n of 0 is going to be C1 cosh of 0 plus C2 sinh of 0. Now we know that sinh of 0 is 0 and that cosh of 0 is 1. So this gives us C1, and that C1 must be 0. So now we have that the x sub n of x must be sinh of n pi x over b. That means that the general solution to this equation is going to be the sum of x sub n of x. It's going to be a linear combination of c sub n, x sub n of x, y sub n of y. That's going to be the sum from n equals 1 to infinity of c sub n sinh of n pi x over b sine of n pi y over b. Now we want to apply the final boundary condition. That was that f of y is equal to u of a comma y. This is the sum from n equals 1 to infinity of c sub n sinh of n pi a over b times the sine of n pi y over b. And what you should see is a coefficient, in this case c sub n times the sinh of n pi a over b, times a bunch of sine terms n pi y over b. And this looks like a Fourier sine series. So doing what we have done before, we're going to want to extend f of y to be periodic with period 2b using odd reflection. That means that c sub n times the sinh of n pi a over b has to equal the integral of, or 2 over b times the integral from 0 to b of sine of n pi y over b times f of y dy. Since what you see on the right, the c sub n sinh of n pi a over b are the Fourier sine coefficients. So that means our c sub n's are going to be 2 over b sinh of n pi a over b times the integral from 0 to b of f of y sine of n pi y over b dy. And that is how you solve the Laplace equation in 2 dimensions. Now I want to go back so that you notice that when we solved the Laplace's equation on the rectangle, that we had 3 of the boundary conditions equal to 0, and those were necessary in order to solve this equation. But you remember Laplace's equation on the rectangle has that the temperatures in the 4 boundaries could all be non-zero. T1 of x, T2 of x, T3 of y, and T4 of y. So if you want to solve Laplace's equation in 2 dimensions, what you have, and you possibly have 4 non-zero boundaries, what you have to do is make 3 of those boundaries 0 and solve the equation, the resulting equation, with the 4th one not being 0. And then you would choose 3 other ones to be 0 and solve that equation. And then you would choose 3 more of the boundaries to be 0 and solve the resulting equation. And then finally, you would take the last boundary being non-zero and the other 3 being 0 and solve that 4th equation. Now, once you've solved these 4 equations, then you can add all 4 of those solutions together to give you the solution to Laplace's equation where all 4 boundaries are not 0. So this is similar to when we were solving the wave equation. Okay.